Hi, NA Physics. It's Mr. Neff back again. Let's finish our talk about standing waves in tubes and answer that burning question, why should you feel sorry for a shopping cart? Here's an important point that I want to make from the last video. So this top picture, this top animation, is what a standing wave in a tube is going to look like. You can see that we have this open tube in this case, and we've got a lot of amplitude over on the ends, and just a little bit of amplitude as you get closer and closer to the middle, and then nothing right in the middle. That's a wave. Now, how are you supposed to draw that? So rather than drawing something like the top picture, what everybody always does is they'll draw something more like this second picture, where they draw what the amplitude looks like as a function of the position along the tube. This is the way we draw it. But the danger is this makes you think that this wave is transverse, and it's not. It's longitudinal. And you can see that it's longitudinal because you can see that the disturbances are moving from end to end, and the vibration of the particles is end to end too. So I'm going to continue to draw them like this or like that, but I don't want anybody to think that this is what is actually happening, that we have a transverse wave here. Nothing can be farther from the truth. This is a longitudinal wave. Now, the reason that we care about all of this so much is because your woodwind, your brass, even some of your percussion instruments are going to be explained this way. You've got instruments like clarinets that are closed on the one end, which is going to be where the vibrating reed is, and open at the other end, which is going to be the bell end. And the lowest note that it can make is going to be this first harmonic note, where a quarter of the wavelength is shown inside of the length of the clarinet. You can also have an open instrument, like a flute, where even though you can't see all the way through a flute, it's open to the air on both sides. You don't put your mouth on the end to play a flute. You blow across this opening. And so all that is to say, it's open on both sides. And so the lowest notes the flute can make is represented by half of the wavelength is equal to the length of the flute. And so now with the flute and any open instrument, it's pretty easy to calculate what the harmonics are going to be, pretty easy to see what the overtones are going to be. Remember, harmonics are integer multiples of that fundamental that give you resonance. And the overtones are going to be those harmonics that are over and above that give resonance. Well, all of that is to say this, that the first harmonic is there's going to be a certain frequency, second harmonic is going to be double that, third harmonic is going to be triple that, and so on and so forth. The first overtone, the next highest frequency that gives resonance, is going to coincide with the second harmonic. Second overtone, third harmonic, and so on and so forth. You should see that that is working exactly like the strings did on a guitar, violin, and so forth. Now, the one that's a little different is the closed open, because with the closed open, you have to have a node over here, and you have to have an antinode over on this side. Now, if I took this first harmonic frequency, let's make the numbers easy. Let's say that frequency was just 100 hertz, fundamental frequency. If I doubled it, I'd get 200 hertz. Now, the thing about it would be if I doubled the frequency at half the wavelength, and the pattern that I would get from that would be node there, and I'd have this thing. And you might say, okay, well, that's good. But no, think about it. That's not good, because what I'd have is I'd have a node on the closed end. That part's good. But I'd have a node on the open end, and that's not going to give you resonance. And so you can see here that the second harmonic, that's 2 times the fundamental, it's not represented on this graphic because it's meaningless. The second harmonic doesn't give you resonance. The third harmonic does, because that's where the frequency is tripled and the wavelength is turned into a third. And so now I have the third harmonic, and that will give me a node at the one end and an antinode at the other end. The fifth harmonic will, the seventh harmonic will. And so the name first overtone, remember, that's a frequency that gives you resonance. It's not applied to 2 times the fundamental. It's applied to 3 times. And the second overtone, that isn't applied to the third harmonic like it is on a string or an open tube. It's applied to the fifth harmonic. So the overtones are frequencies that matter. ones that are over and above the fundamental that give resonance. And you're only going to get resonance if you have those node, antinode, closed end, open end conditions satisfied. Now, I'm showing this as with a clarinet and a flute, but don't think that the tubes have to be straight, because on most instruments they are not straight. On a trumpet, the column of air actually gets wrapped around before it makes it to the outside. It's okay. On a French horn, it gets wrapped around a really lot. And the other thing too, don't think that it has to be what you'd call a bona fide instrument. It could be something like this wind chime. Wind chime is going to be open tubes of different lengths, and they're going to make different notes. Okay, how about just a couple examples before I let you go? So on this one, it says a tube with a cap on one end, but open at the other end, has a fundamental frequency of 130.8 hertz. Give you the speed of the sound, what we're used to, 343 meters per second. Part A says if the cap's removed, what's the new fundamental frequency? And part B says how long's the tube? I actually think it's a little easier to understand to do part B first and then follow up with A, so that's what I'm going to do. So I'm going to say in part B, we have the tube, and it's going to look like this. And so it's got the cap on the one end, and that means that's a node. And over on the other side is an antinode, and so I'm going to draw that over here like this. Remember, this is a graph of what the amplitude looks like or what the pressure is doing, not what the real wave looks like. Okay, and so they want to know how long the tube is, L. Well, I can see one thing, that the length, 4 times the length of the tube is equal to the fundamental wavelength. And you know what? I can calculate that fundamental wavelength pretty easily because they told me the fundamental frequency and they told me the speed of the sound. Remember that the speed of the sound is the fundamental wavelength times the fundamental frequency, or 2.2 or 3.3, whatever you like. And you'll see that on the next example. So the fundamental frequency, the fundamental wavelength is the wave speed divided by the fundamental frequency. How about 343 meters a second by 130.8 hertz? And if you multiply that out, you're going to get a fundamental wavelength of 2.62 meters. Now, that's not what they asked for. They asked for the length of the tube. And so I'm going to say that the length of the tube, 4 times that length of the tube, is the fundamental wavelength. So the length of the tube is that fundamental wavelength divided by 4. So I'll take this 2.62 and I'll divide it by 4. And I'll end up getting a 0.655 meters. Now let's go back and finish up part A. With part A, we have the same tube, but it has the cap off. And so now it's going to have an antinode on both ends like that, but it's still the same length as I said. And so now I'm going to say that 2 times the length is equal to that fundamental wavelength. And so that fundamental wavelength is 2 times the 0.655 meters, which is going to be a 1.31 meters. Now they want to know what the fundamental frequency is, and so the fundamental frequency is going to be that wave speed divided by that fundamental wavelength. So I'll take my 343 meters a second and I'll divide by that 1.31 meters, and I'm going to get a fundamental wavelength this time of 261.6 hertz. How about 262 hertz? And maybe you saw that coming. Maybe you said, well, hey, the fundamental wavelength is going to be half as much, so the fundamental frequency is going to be twice as much. And one last example before we go, we've got an organ pipe here. It's open at both ends. It says it's producing sound at its 3rd harmonic, and the frequency of that is 262. They give us the speed of sound that we're used to, and what's the length of this pipe. So the 3rd harmonic is going to look like so, and you can see there that we have 1.5 waves in here. Here would be 1 wave, and then I have another from crest to trough, so 3/2 of a wave inside of there. So I can say that the wave speed is, well, it's true that it's the fundamental frequency times the fundamental wavelength, but it's also equal to the 3rd harmonic times the third wavelength, like this. Now I can solve for that third wavelength. I can say that third wavelength is the wave speed divided by that third harmonic frequency. So I'll take that 343 and I'll divide by that 262 hertz, and that will give me 1.31 meters. Now you see something here. From the picture, you can see that 1.5 wavelength threes is how long the tube is, and so I can take that 1.5 times my 1.31 meters to get the tube's length, and that tube then will be 1.96 meters. Now, I think that's a good way to do it, but some people would think it through just slightly differently, so humor me here and let me see if I can show something that the rest of the crowd would like. Some people would have said, all right, hey, that frequency 3 is 262 hertz, and that means that the frequency 1 is the 262 hertz divided by 3. And they would have done that as 87.33 hertz. Now they're going to look at that top picture and they're going to say, all right, in that top picture, which coincides with that 87.33 hertz, they're going to say, hey, in that picture, I see half of a wave in that length, or the 2 times the length is equal to that fundamental wavelength. So that length is that fundamental wavelength divided by 2. So what is that fundamental wavelength? Well, it is the wave speed divided by that fundamental frequency. So that's going to be that 343 meters a second divided by the 87.33 hertz, and so that fundamental wavelength would be 3.93 meters, and now they'll take that and divide it by 2, and they get the same thing. Of course they do, 1.96 meters. So just 2 different ways of looking at the same thing. Hey, before we go, why should you always feel sorry for shopping carts? Hey, they get pushed around.